Good morning. Welcome to the GI Lecture and Education Series. I'm Jerry Dussault, and I'll be your host and moderator for this presentation on deepfakes, revealing the foundations of deceptive machine learning. We're very pleased to have Dr. Robert Wright as our speaker this morning. He's a principal research scientist with Assured Information Security and group lead from the Advanced Research Concepts team. He serves as the principal investigator for multiple DARPA and AFRL efforts, including the Victors effort that is developing novel machine learning-based biometric verification techniques for cyber attribution. In 2014, he received his PhD in computer science from Binghamton University for his work in developing reinforcement learning algorithms that learn efficiently from experience. His work has been published in many top-tier scientific venues and was awarded Best Paper at the 2013 European Conference on Machine Learning. Prior to joining AIS, Dr. Wright was a computer scientist with the Air Force Research Laboratory and co-lead for the Autonomy Community of Interest Machine Perception, Reasoning, and Intelligence Technical Challenge Area for the Office of the Secretary of Defense. His research interests include reinforcement learning, machine perception, generative adversarial networks, multi-agent systems, and genetic algorithms. Due to technical error, I failed to record the first few minutes of our lecture when it first aired on 17 December. I'm re-recording this introduction on December 20th and will flip through Dr. Wright's first 3 slides for you. We'll then join Dr. Wright's presentation in progress on chart number 4. Please give me a moment to bring up Dr. Wright's material. Again, my apologies for the missing audio content, and we will now join Dr. Wright's presentation in progress.
Networks, which are based on neural networks, which have foundations dating all the way back to the 1960s with perceptron networks. And what they are is an abstract, very loosely tied model based on how we understand animal brains to work. And it's not nearly as advanced as an animal brain, and not really a good model, but it works. So for deep neural networks, a lot of this is based on, or how they work is based on hierarchical feature extraction. So a deep neural network is defined as a neural network that is beyond 2 to 3 layers deep. So in this example, we have a 4-layer neural network where input comes in and then is parsed at various levels of abstraction. And at the end, we are able to predict a function in here. So in this case, we give it pictures of faces, and on the output, we want to detect where the face is, eyes, and labels like that. So with a large data set and the right amount of labels, we're able to take advantage of what's known as automatic feature extraction, where instead of using handcrafted features that would define how to identify the face, the machine itself is able to use the error signal and how it was able to work with the training data set to actually figure out how to identify a face. So at the earliest levels, it identifies things like edges and shadows. At successive layers, is able to figure out how to compose them into different facial features like eyes and noses, and then finally things like full faces. And the power of this is that it's no longer at the mercy of how well we understand how to describe the environment. It's able to figure it out, and this combined with large data sets and very, very cheap high-speed computing like graphic processing units has led to a renaissance in machine learning and real practical useful machine learning, like a cat detector. And to get a sense of how fast things are moving on this, all we have to do is look at the performance over time. So what I'm showing here is performance on the ImageNet challenge problem. So ImageNet is a large object identification and classification task. There's a large data set of over 14 million images annotated with what they are. And since 2010, it's been a standing, well, since 2010 up until about 2018, it was a standing challenge for artificial intelligence, computer vision, with a yearly challenge to see how effective things, how effective the methods were. And what we're seeing here is a chart of the top 5 accuracy on how well the different algorithms were at identifying things within the images. And so before 2012, things weren't all that great. We were around 75% accuracy using the latest and greatest methods. In 2012, one of Jeffrey Hinton's students came up with this convolutional neural network based architecture called AlexNet, which was like the very first deep neural network aimed at this task. And it was a huge leap in performance. And after 2012, it didn't take very long, around 2016, for the algorithms to catch up to humans and then exceed humans in their level of performance. So it's not just with image recognition, this phenomenon of deep neural networks, machine learning exceeding human level performance on some certain tasks is happening in a lot of different places, and it continues to grow. So once we had large, powerful models like this, it didn't take very long for researchers to figure out some very interesting and somewhat devious things to do with them. So with good classification networks, we started to see an emergence of what I'm going to term as the early deep fakes, the ones that use kind of discrimination models in designing how they work. So one that we see, you'll see a lot of examples out in the wild on, can't come from this paper of face-to-face, which was able to take advantage of a deep neural network architecture called an autoencoder to produce very realistic face swaps, where you could take the face from one individual and then replace it with someone else, anyone else. So the way that this system was able to work is it takes advantage of this encoding architecture where you can use a deep neural network to abstract a phenomenon into a low dimensional, relatively latent space that describes what's in the image, and then from this low dimensional space you can then reconstruct it into the higher dimensional original space of where things are. And to achieve this swapping, what they do is they use 3 deep neural networks. One encoder that can encode images from both the source and target and project it into this shared latent space, and then 2 decoders that learn how to do the translation from this shared latent space. So after you've trained it on both, the encoder can learn this mapping, and then you can follow a path through the encoder from the source to the target and generate images like this, where a reporter from Ars Technica replaced Mark Zuckerberg testifying to the Senate panel with a image of Brent Spinner as Commander Data, and it is done fairly effectively. So this is pretty convincing, and yeah, this was a reporter who had not a ton of training in this and was able to do it within 2 weeks. So these things are readily available and you can do it. However, it produces some noticeable video artifacts, and it's kind of limited to the amount of pose and range of movements. So, still very convincing, still very interesting, but can we do better? And yes. So things that are coming out now are based on advances in generative modeling. So a lot of the advances in deep learning and the applications that we've seen have been related to what what are known as discriminative models. So these are things that classified supervised learning types of tasks where the model is learning what is and what isn't a thing. So in this case, for this example, what is a face and what's not a face. And what the discriminative model is doing is it's trying to learn this hypersphere of everything that inside of it can be considered what we're interested in this case, a face, and everything outside of it is not a face. And all it's trying to do is discover what are the boundaries of this hypersphere. And so, like I said before, this is related to standard supervised learning methods for classification and regression. And as I showed before, these models are getting really, really, really good, sometimes better than human, at defining these boundaries simply by be given examples in a data set of the phenomenon of interest, in this case a face, and label data of what's not a face. What up until fairly recently, with advances in generative models, what discriminative models or machine learning wasn't very good at the time is trying to produce phenomenon from this, so generating things. So a generative model, what it is learning to do is how to describe what's in this sphere. And so examples are things like decoders. So if I were to say, please give me some arbitrary face within this space, show me what this face would look like if I say I want that. And before, you'd get something that wouldn't necessarily look even as good as this. It'd be fuzzy. The features of it would be in weird spots. It wouldn't look right. So with just a reversal of traditional methods of how things would go back. Then the reason for this is that even though the discriminator did a good job of figuring out how to encompass the training data within it, it wasn't really given the full perspective of everything that goes into here or how it is structured based on just standard supervised learning techniques. And all this really kind of changed in 2014 with the advent of generative adversarial networks and a new training process invented by Ian Goodfellow or introduced in 2014. And this concept of adversarial training works like this. So instead of just training a discriminative or a generative model in isolation, you use two networks, and you train them both in opposition to one another. So in this framework here, we have our neural network discrimination model, which is like the supervised methods that we've gotten very, very good at developing. And then you have kind of an inverted method, but not necessarily inverted, but you have a generative model that is supposed to produce phenomenon that we're interested in. So in this case, faces. So we have source data of lots of different faces that we're interested in modeling, and we want this generator to produce something that approximates what's in here. So with adversarial learning, what we're going to do is we're going to feed the discriminator lots and lots of images of what we're trying to model. And at the same time, we're also going to be feeding it lots and lots of examples of what our generator is saying should fit within this space. So we're going to sample from points in this hypersphere, what should be a face, and our generator is going to imagine what is a face. And we're going to feed both positive and negative examples to the discriminator. And the discriminator is going to use its very effective means for modeling these phenomenon to differentiate what's real and what's fake. And when it's doing that, it's learning the key features for defining this, but also the key features for identifying what is fake. So that could be the end of the story, but what we want is this generator to be good at synthesizing these things. And the way that we do that is we tell it when the discriminator was effective at identifying things that it produced, and the discriminator and how it works with the neural network as being a differentiable function, we can actually explain to the generator exactly where it was wrong. So that the next time after this is done training on what it got wrong, it can produce an effective face or an effective phenomenon to reproduce. And this gives us a way of very powerfully synthesizing any type of phenomenon. And another added bonus of this is because the generator is challenging the discriminator, and the discriminator is getting more of an understanding of what is in this hypersphere, what defines a face. we get much more effective featureization and a much higher level of control, which enables us to do things like this, where we can define the exact pose, style of the face, move things around. We can add an inverse mapping where we take a source image of a real thing, map it into this space, and then tweak the feature so that we can do things like a gender swap and things that look real. So it not only did it change Daniel Radcliffe's face to be a little more curved and add long hair, it changed the eyebrows in ways that look sense. It made the lips fuller. It changed the structure of the nose to match the gender because it understands what would make a realistic looking gender change. So with that said, let's examine what can be faked with these powerful methods. And it'd probably be easier to say, well, what can't be faked? Because most things can be faked. Obviously, you'll see lots of examples of images and videos that can be done very, very convincingly. You could spend many hours, which I have, browsing different examples on YouTube of things that have been interesting things that have been done, such as I like a lot of the stuff done by a YouTuber known as Control Shift Face, where he will take movies and swap out the actors for different ones. This is one of the earlier ones where he took The Shining and traded Jack Nicholson for Jim Carrey, which Jim Carrey could probably do that role pretty well. It's very convincing. I highly recommend people check that out. So that's what a lot of the examples are, but you're seeing more and more now in the area of audio generation. So not only can you swap faces, but you can swap audio. And this is an area that I was examining more to see what's been done in preparing for this talk. And this is something that has changed a lot since I last gave this talk. So at this point, I discovered that there's a tool available online right now that someone already put the pieces together necessary to do a full voice synthesization, where you can actually type in what you want someone to say, and if you have a recording of just 5 seconds, it's able to learn or it's able to project that into an embedding space of what that voice should sound like for different things, and you can have that voice to a fair degree of reasonableness say anything you want. So let me click on
it is possible to download all the required materials and duplicate anyone's voice in under 2 hours.
So we have some fun plans for our company Christmas party for that. And so not only can it be used to synthesize voices, but there's been some amazing work done by OpenAI, and I have some more examples of this, to synthesize things such as music and different types of audio phenomenon. There are companies like Lyrebird that offer this as a service for virtual assistants to make interacting with computers a bit more personable. And there have been some examples in the wild of people using this exact technology to fool people into moving money around. So this is in the wild, and it's good. But I think one of the thing that I was most surprised by is the advances in language models and their ability to produce realistic looking text and language. So in 2018, I believe, OpenAI came out with a language model that could produce realistic looking text and sequences called GPT-2. And they were surprised at how effective it was at producing articles or just different types of text in a convincing manner that they didn't want to release it. And then some grad students took it upon themselves to, based on the paper, reproduce the results, and were able to do that, which led to OpenAI releasing GPT-2 just because there was no point. But since they did that in 2019 and more recently in 2020, they made even greater headlines based on their improved model GPT-3, which doesn't change the overall architecture. The architecture is based on a type of neural network known as a transformer, which uses sequences. So language can be thought, the sequence of words. It's able to take an input sequence, and based on short samples of it, it's able to predict in the future, what is the most likely continuation or ending of the sequence. So there's more details on this link on how that works. And so GPT-3 was a much larger model containing 175 billion tunable parameters that OpenAI trained on a very large corpus of data that they extracted by basically scraping the entire internet and Wikipedia and such. And they were very impressed by its ability to again, reproduce text, but not just text, reproduce text, but maintain context. And what they did was they opened it up to a bunch of researchers that they knew to see, what they could possibly do with such a system that can understand text to a very, very high level. And some of the things that came out of that study was fairly amazing. So here I have an example of what a researcher was able to do, where they faked an interview with Albert Einstein, where all they did was told the system, hey, I want you to pretend that you are Albert Einstein, and they ran an interview where Manuel is the interviewee and Albert is played by the part of OpenGPT or GPT-3. And what's amazing here is Albert, the AI, is able to understand and the questions that are coming in and understand how to respond from Albert's perspective, with not just his language style, but where he is, what the year is, certain things that it was able to extract from the articles that it reviewed, how he came to the United States, what his religion was, what was going on at that time, and it was very convincing. And I will say that this is a cherry-picked example. There are certain things that it can't do, but this was kind of astonishing. And so it went beyond that. So even though the system was kind of trained in a task-agnostic fashion, it was able to use its understanding of human language, or the English language, to do some, other amazing things. Where this example was able to use it to create a face generator, where you describe in English what type of face, using a generative adversarial network on the back end, you would like to see, and it was able to map from the English description to the features in the generator space, and produce things that are obviously what the person is asking for. So lots of really amazing developments, and I highly recommend to those interested going through the articles that are on there to see what is possible, because there's a lot of very interesting things going on. And so there's also been some studies to look at how believable and how effective these things are. And I will say that this slide is outdated. So I haven't made any changes to this one in a year. So it's only gotten more effective, I would say, or much more effective since I first collected this material. So on the left here, what we're looking at is the overall believability and effectiveness of articles generated by both human and a language model. In this case is Grover, which is not nearly as effective as something as GPT-3. So that's looking at style, content, and the trustworthiness. So on real topics of real newsworthy, you can see that it's roughly as effective and as believable as a human is. And when it comes to propaganda or generating fake news, it turns out that the machine is actually a little bit better at lying than the humans, and overall still very, very believable in comparison to the real ones. And we see more of that here when we look at things like the face swap applications or the deepfakes with videos or images, where these researchers looked at several different algorithms and the user's ability to pick them out. And so what's interesting here is once you get around 50%, that's at the point now where you can't really differentiate between what is real and what is not real. And so we are definitely already at that point, and it's, you know, it's difficult to tell at this point what is real and what's not. So go into the applications, and you know what are different ways that we could use this, and what is the, you know, impact on us as a society. So for applications, the first one that comes to mind is you know, these things are really interesting and fun, allow for some interesting what ifs.
How's your head?
Oh, good. Fine.
Oh, I've been so worried about you ever since you ran off the other night. Are you okay?
Come on, we're tardy.
I'm sorry, I have to go.
Come on.
Isn't he a dreamboat?
Doc, she didn't even look at him.
This is more serious than I thought. Apparently your mother is amorously infatuated with you instead of your father.
Whoa, wait a minute. Doc, are you trying to tell me that my mother has got the hots for me?
Precisely.
Whoa, this is heavy.
There's that word again, heavy. Why are things so heavy in the future? Is there a problem with the Earth's gravitational pull?
What?
The only way we're going to get those two to successfully mate is if they are alone together. So you've got to get your father and mother to interact in some sort of social...
Well, what, you mean like a date?
Right.
Well, what kind of date? I don't know. What do kids do in the 50s?
What? They're your parents. You must know them. What are their common interests? What do they like to do together?
Nothing.
So very convincing. I think Disney's going to be doing a lot with this. They've already shown that the deepfakes generated by this are a bit more effective than the CGI characters. I expect to see a few more dead actors reprising roles for various things. So there's that'll be interesting, and that comes down to where I see most of the positive, I guess, roles for this type of technology coming into play is in content creation, using this to help us generate new media, new things, or more effective media. So things like AI assistants like the Google Duplex technology, which can place phone calls, like order reservations on your behalf. And if it wasn't for the fact that it would announce that it is a robot, you would be hard pressed to say whether or not you were talking to a real human on the other end or not. Virtual worlds for games and movies, so procedurally generating whole worlds or gaming environments for a player to explore, or allowing the special effects artists to just specify, say, like the GPT-3 model, hey, I want subtype of alien worldscape with these types of details, and instead of having to generate all of it on their own, the computer can do most of the busy work, and it's just up to the special effect artists to like generate the details. The same can be used for software development. So say I want a web page, and there's some examples of GPT-3 doing this, where you can say I want a web page that has things of this nature on here, I want it to be red, things like that. You can just specify, and then it's just up to the software developers to add in the details on the back end, or just fix some minor errors. I have a lot of interest in how this can be used for artificial intelligence. So things like reinforcement learning require a lot of experience to learn from. And unfortunately, that requires usually simulation, high fidelity simulation environments, which aren't readily available. But this type of technology would allow for the AI itself to learn accurate representations of how the world works, in which the AI to explore and test out things and figure out how to act within those environments. So art and architecture, and just in time for Christmas, even music. So this example was generated by the OpenAI Jukebox. It was told to generate music in the style of Frank Sinatra, and it also invented the lyrics. have a listen.
It's Christmas time and you know what that means. Oh, it's hot tub time. As I like the tree this year, will be a tub. Oh.
So that was fully synthesized, the text, lyrics, music, all of it. Somewhat interesting and scary. So another area of application that I see this having a huge play in is in cybersecurity, both to detriment and enhancement. So not only is this effective at fooling humans, but it can also be extremely effective at fooling machines. So one of the obvious uses of it is in the targeted misclassification and detection systems. So as an example, here we would have something like an image classifier, which can accurately detect things like this is a giant panda in there, but with targeted misclassification and an understanding of how this classifier works, we can adversarially introduce or learn a mask that can make somewhat of an imperceptible change to the image on the back end when you apply this to it from the human's perspective. But because the machine is using different features and trying to come up with this classification than a person would, the machine comes up with an incorrect classification of this being an American black bear. And this can be done at varying degrees of success, where you can actually specify exactly what you want to be misclassified as. And depending on how far of a stretch it is, it can be extremely hard to see it from the human perspective. Also, we're probably going to see, using this technology, some larger scale, more convincing spear phishing campaigns where we can use, or the adversaries can use this technology to create hyper-personalized, convincing attacks that to get people to reveal certain information that the attackers can then use in later campaigns. But this is a double-edged sword, so this can also lead to enhancements. Deceptions go both ways, and we can create much more elaborate, realistic-looking defenses than to use to kind of snare would-be malicious users that are trying to attack our networks. And also, we can use this adversary techniques to harden our detection system so that kind of the low-hanging, easy-to-use systems are easier to detect when applied against our systems.
Bob, if I could interrupt you for just a second. We have a question related to these types of spear phishing attacks. Do you think we'll see a rise in ID theft, criminals 3D printing deepfake latex masks similar to the eerily realistic Danny DeVito hyperflesh mask?
So there's a lot of in that. So I do think, just in general, we are probably going to see this in play in spear phishing campaigns. I don't know about the flesh example of going through the trouble of doing that. Things like just like video filters, I would imagine are a bit easier to do than actually trying to 3D print someone's face. But yeah, Mission Impossible style, generating a mask, possibly doing something like that. I could see that. That's an interesting question. Thank you. All right. So also, this is probably going to be used quite a bit in disinformation. So generating realistic looking fake news. Public figures saying things that they wouldn't
During an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things.
So here I have two examples that you can find readily that are more public service announcements. So in this one, we have Barack Obama being deepfaked using text from Jordan Peele, kind of just highlighting how effective these things were a couple of years ago, and how to, you should need to be aware of these things. And then more recently, Matt Parker and Trey Stone of South Park fame released their own, also kind of public service, but more political satire stuff in their own style. And I'm not going to share this stuff because it's their style. of examples that are, even more convincing in terms of their realism, but not so much in their content. And so this could obviously be used for this very timely and very serious problem. It's already a problem even without these things, and this is only going to make it that much worse. So I already have problems with my mother-in-law believing everything on Facebook. This is gonna make it much worse. So I do anticipate we'll see more and more of this, and how to, combating this is going to be a problem. And if it will let me progress slides, but I think it's going to have a much bigger impact, I think, on our legal systems. So with the ability to almost, or in the future probably with certainty, being able to synthesize and manipulate any media to the point where it would be very difficult, if not impossible, to determine the difference between something synthesized and something actually, what is admissible evidence as media anymore? Can media be verified? These are questions that are going to really challenge our legal systems. Does the existence of deepfakes lead to reasonable doubt? And also, I don't think that it's unreasonable to say that these things, to an extent, need to be covered by things like the First Amendment. But their use, what is the limitations on their use? How should their use be regulated? And so these are interesting questions that our current legal scholars are trying to wrap their heads around, and are at the moment kind of struggling with. We'll see where this goes. So we've seen what they can do, how big of a problem they are, what's being done, what possible things are out there that can be used to mitigate them. So the first thing is, there's a lot of efforts being proposed and being pursued right now in detection schemes. So both Google and Facebook have released data sets and challenges to inspire people to come up with different ways of detecting deepfakes, novel ways of doing this. In fact, DARPA released a year or two ago now the DARPA Semaphore program, which is looking at this exact problem, and they're trying to use semantic and contextual variations that deepfakes at the moment aren't great at doing, at handling, such as getting the earrings on both sides of the face to be symmetrical. However, with time, these systems might surpass that. In fact, there's a double-edged sword with trying to come up with technological detection systems on this, in that it is the detection systems, going back to the generative adversarial network examples, that enable the very, very good synthesis. So once you build a good detector for the system, you've actually created the means for the next generation of generative models to surpass or fool that detector. So unless the detection systems are kept completely secret and there are no outputs from it, it's unlikely that a generator couldn't be engineered to surpass those things. So that's a caveat with that, going that route. Also, there's been some work in trying to fingerprint these synthetic generation techniques. So with these models, or with these deep neural networks, based on the specific data sets, the specific model architecture, and the specific training regimen that was used in to develop them, these models will exhibit unique artifacts or things that exist in it because of the bias in both, or all the data, the model, the architecture, things that are prevalent in all the things that they produce. And these unique artifacts could be used as a fingerprint for once they've been identified, that could be detectable and be used to attribute who's doing what, because there's probably going to be quite a bit of reuse. Data is expensive to gather. The model architectures can be varied, but generally there's like a few good ones that are good at modeling those domains. And depending on the complexity, training these things can be very expensive, in the orders of millions and millions of dollars in just the computing time and resources used to generate these models. So these things are bound to get reused, and we might be able to use these and their fingerprint as an attribution, or even figure out how examples like this were generated. So what I'm showing here is that the authors of the StyleGAN model were actually able to identify, using the detection, some of these artifacts that I'm talking about, things that were prevalent in all the examples. And so this type of phenomenon is of interest to a lot of different organizations, including AIS, and some DARPA is looking at this point. So this is something coming up. And then finally, or not finally, another avenue is the regulation and legality. And so this is a threat that the US government and different organizations across the world are paying attention to and trying to actually address. So something that Congress is actually able to pass is like the Deepfake Report Act, which is increasing regulation and increasing the amount of funding for Homeland Security to invest in trying to address this issue. Just a few weeks ago, even New York State was signing laws on how to regulate or control the use of deepfake technology. So government and the legal system is starting to catch up, and organizations are trying to understand and how to effectively and responsibly use this technology. So there is some hope for this, and stay tuned. But the most important thing for addressing this as a problem is just to be aware of it as a potential problem and maintain healthy skepticism when viewing media or reading things in the wild. Don't disbelieve everything you see, but at the same time, understand that these things are out there. Enjoy the YouTube videos and all the really interesting things that are going on, and just, educate others and, what is out there and what's possible. And so with that, I'm going to end the presentation, and I appreciate everyone's attention and joining me for this talk, and I appreciate the GI inviting me to present.
Thanks very much, Bob. We're a couple minutes over, but I want to give one more question from one of our viewers, and that has to do with things that we can do to preempt these types of deepfake attacks. Given we know no system is invulnerable to penetration, our national security systems, you talked a bit about mitigating some of these deepfakes, but from a preemptive standpoint, are there things we can do?
So depending on, that one's hard to answer without a little more context. So I can take a shot, and then we can try to clarify the answer on that. So things like the detection systems that I was talking about before, like if we have a system in place that uses deep neural networks that an attacker might go after, and we know that an attacker might try to fool our system, we can use we can try to red team it using this kind of adversarial training against it in the first place, to kind of get an understanding of where it might be attacked, and even possibly get signatures for things out in the wild that an attacker might use as part of the toolbox for things that would go against it. So this is an idea that we've kind of floated around a bit. It's not something that we're actively working on, but I want to say that, to anyone in the audience, if you're interested in this type of thing and interested in pursuing more research with us, by all means, contact me and we can discuss some ideas on how to possibly address issues like this.
Okay, great. Thanks very much, Bob. My apologies to our audience for running just a couple minutes over time. I'd like to wrap this up, let you know, remind you that we will try to make this material available via our website and YouTube channel. I'll be sending an email message to all of the participants who registered, and I'm sure you have my email address. If you have follow-up questions, let me know. I'd really like to get feedback, and I will extend an offer in on a follow-up email to everyone how you can obtain a copy of these presentation charts and requesting feedback. So one and all, thank you for attending our presentation this morning. I think the record reported snowfall is about 9 inches from the Pittsburgh area. I listened to the Weather Channel as my background noise in the morning, and I heard they got about 40 inches in the Binghamton area this morning. So it could be a lot worse, I guess. So with that, thank you all, and I'll bring this webinar to a close. Have a great day and a happy holiday.
Thank you.